here's what really happens inside of the computer. And by really happens, I mean it's a pictographic analogy of what really happens. So there's stuff on the stack, and when it calls into main, so now this word main actually represents the return position of where to go to when you're done with main. Does that make sense? Okay, so we're inside of main. Now you'll notice that main actually takes a parameter. This is actually an array called args. So there's actually something on the stack called args. And args is pointing off to something that's off here on the heap. And that something that's off on the heap happens to be an array of strings. But we're not going to worry about that for right now. We'll come back to that later. Okay? Now, after that parameter, I say int I. Remember what that does? That actually pushes something onto the stack named I. And it's going to hold a value of 0 because it's initialized to 0. And after it executes that part of the line, it'll execute the other part of the line where it says equals 3, and will then change that number to a 3, right? Then I call foo of I. Well, it's going to put foo on the stack. And by foo, I mean it's going to remember this is where you are. You're right here where we call foo, and that's where it's going to come back to when it's done calling foo. Okay? Now, there's a thing called x right here that's a parameter. Parameters also go on the stack. Therefore, there's a thing called x there. And it's going to have a value of 3. There's actually only a 3 on the stack. X is that's for my own knowledge, right? The compiler knows it's called x. The compiled code doesn't even have an x in it. Actually, truthfully, it does, so you can attach the debugger to it, but it doesn't have to. If you compile C code, it loses all the variable names. Java keeps them for various reasons. There's a thing called reflection. Lots of stuff I don't need to tell you about right now, but I'm hinting that there's more coming. For right now, makes a box, throws it on the stack, and there's going to be a 3 in it. Do you see that this 3 is not the same as that 3? They are different 3s. Yes, question?
Can you go over where x exists on the stack before foo is called?
X does not exist on the stack before foo is called. Yeah, at the moment you call foo, it's going to push 2 things onto the stack. So the computer's doing a little bit of work. So let's back up. We're going back in time to, we have just completed this line of code. And this is what the stack looks like. And by the way, there's an object over here at the end of args. Okay. And now the instruction pointer moves on to this line. And this line says, oh, look, we're making a function call. So the way we do a function call is, the first thing we push onto the stack is, we think to ourselves, we're going to need to get back here. This is our finger in the recipe book. And so I'm going to write the word foo to remember we're on this line that calls foo. And as soon as we return from this call, we're going to get back to the same position. So this thing on the stack is just a number. Everything on the stack is a number. Everything in your whole darn computer is just a number. That number is the memory location of where the code is. It's the pointer into the instructions. It's called the instruction pointer. And think of it like this. When you're baking a cake, you put your finger on step 1, you do it, you move your finger to step 2. You do it, you move your finger to step 3, right? So this is where the instruction pointer is. And we're going to need to come back here, but I'm moving my attention up to this foo. So this is where my finger is going to come back to when I'm done, but for right now, the instruction pointer moves all the way up to right there. That answer it? Okay. There's also a parameter here. So when we push foo onto the stack, we are also going to push another slot onto the stack that holds a 3, and it's going to be called x. That might be a better way to write it. So there's a slot on the stack that holds a 3, and I refer to that slot on the stack that holds a 3 as x. Okay? Notice that x and I are not the same slot, but they hold the same number for now, until I execute this instruction right here. As soon as I execute that instruction, it says x++. What does that mean? It means change this number to a 4. Notice that number down there called I did not change to a 4. Okay? Then we print len x, so it's going to print whatever's in this slot right here on the stack, prints a 4. And then we hit this closing squiggly brace. I should just call them a bracket or brace. Brackets are square, braces are squiggly. You don't have to call them squiggly braces, they're just braces. It's a habit. But it's more clear, isn't it? Okay, that is an implicit return function. In fact, what happens, I think, is the compiler injects a return because I didn't actually state return. I've reached the end. What return means is pop everything off of the stack until you find a return pointer. So that x is going to go away because it's not a return pointer. That foo is a return pointer, right? That's where I was when I called foo. Therefore, it pops that off the stack too, and that tells me to restore my instruction pointer to right here. Well, actually, the end of that. So it's really right here. And now it continues execution. And notice the stack now looks like this. There's no x on the stack anymore. X is gone. X only existed for the duration of while it was calling foo. And more specifically, it existed when the instruction pointer was here and there and there and there and there. It existed from brace to brace. Once we hit the closing brace, this x was gone. And now we reach this line of code. That's why it can't print x. It doesn't know what the heck x is. But we can print I, and I has a 3. And it has no knowledge that x was ever 4. It doesn't even care what x was. All it knows is I is 3. So it prints the 3. And then we hit this closing brace, which says pop everything until it hits a return position. So it pops that I off of the stack, pops that args off the stack. The garbage collector comes in and picks up that garbage because nothing's pointing to it. We'll talk more about that later. We pop this off the stack, and this actually is a return pointer. And finally, the instruction pointer is right here on this line that is doing something that was even before your program began executing, and the computer's right back to where it started, and it continues. Question?
Can you explain again what the return line does in the foo function?
Yes. Return pops things off the stack until it finds a return pointer, a place where its instruction pointer was before when it made the call. And it pops that off too, and that tells it where to restore its instruction pointer to. And then it keeps on going. So for example, you could have a call within a call within a call within a call. You can nest them arbitrarily deep. And all that happens is the stack gets piled up with a whole bunch of return values. And when it finishes a function, it just looks on the stack to see where it left off. And it keeps on looking to see where it left off until it's all done. Did I answer the question?
I'm just trying to figure out, so say we run the program, would it print out 4, 3, then 4? I'm sorry, 4, 3, then 3 again?
So this program only prints 4 and then 3.
Okay.
Because there are 2 printlns, one there and one here. If you printed another one like that, it would print 4 and then 3 and then 3. And if you did foo of 7, then it would say 4, 8, and then, no wait, it'd say 4 and then 3 and then 8 and then 3.
Okay.
Is that, okay, cool. Question?
So is that a convention in Java that even if you have a void function that's a void, you have to add the return line?
The compiler will add return automatically for you. If we omit it, it's just as if we didn't omit it. It puts it in. I never say return unless I'm returning a value. So if you say int there, then we have to return 11 or some int value. If you forget the return when you actually have a value there, the compiler is going to yell at you because it doesn't know what you want to return. By the way, you might ask, where do return values go? As it happens, they go on the stack too, and that's how things communicate. It basically pops off the instruction pointer and then pushes on the return value, and then the caller knows to pop that return value off of the stack so that it can use it for whatever purpose it wants to use it. So local variables go on the stack, parameters go on the stack, instruction pointers go on the stack. You get what the stack is there for. Okay, any other questions? Well, now here's something. Shake it up a little bit. What if I say, instead of taking an x, a foo takes a sum class named x. And just so we can print something, let's call it int val. Okay. So now here I'm going to say sum class equals new sum class. Wait a minute. I got to give it a name, don't I? How about SC for sum class? But this one's an object. Let's call it obj. Okay. I made an object named obj of type sum class, and I put it on the stack. Heap. Obj is on the stack. The object is on the heap. The object points at the stack. Okay, I'm going to draw the whole darn picture. This will make a variable named obj. The new sum class will make an object. Equal sign will connect them. We talked about this last time, right? Okay. Now suppose I call foo of obj. What does that do? Well, first it puts the return position on the stack. And by the way, I know I forgot main and args, but I'm not being totally complete right now. Then it's going to put an x on the stack. And what is the value of x going to be? Remember, the value of obj is actually a number. That number is the memory location of that object that's on the heap. It's the pointer to that object, right? And remember, stuff on the stack is copied by value. So we copy the value of obj, which is the number of where that thing is, and put it in x. So in other words, x is going to be a number that also tells where that same box is. With me? Okay. Well, now suppose in here I say, can't println x. I can println x.val though, right? And now suppose I say val plus plus. And then while I'm at it, let's come down here and we'll println obj.val. See that I could write this code? What will this program print to the screen? Let's see. Oh yeah, initially it's going to be 0 because val's initialized to 0 in Java. In fact, that's bad code that I didn't initialize it. So heck, let's initialize it to 3. So we make a new sum class. Sum class.val is 3. Where does that 3 go? It means there's a little spot right here for a number. In that, there's a 3 right there. Ah, come on. Show me. And this place is called val. That is really hard to understand and see because of my messiness. I try again. There's a 3 called val. And it's inside the object of type sum class. Notice that x and obj point to the same thing. So this line of code right here that says val plus plus, the compiler actually comes in and says, oh, you mean this dot val plus plus, because there's no local variable named val. It's going to increment val, so that 3 is going to turn into a 4. Actually, it will have printed it when it was a 3, but then it will change it to a 4, and then it will return. When it returns, what will happen? The usual stuff. Pop everything off the stack until it finds a return position. So it pops off x. That pointer just goes away. Then it pops off foo. Wait a minute. No, it doesn't. Foo is the return pointer. So it pops that off, and that tells it where to go. Now it's back here. And now we're going to print out obj.val. What is it going to print? It's true, we don't return anything. Oh, fine. Now what's it going to print? It's going to print a 4. The reason it's going to print a 4 is because obj.val is 4. And you might say, wait a minute, last time it didn't leave it changed, and this time it did leave it changed. What's the difference? Yeah, well, I passed by reference this time. Remember, all primitive types put their value on the stack. All class types make these things, objects that are out there on the heap. If you leave it on the heap, it's just going to sit there on the heap till you change it. If you leave it on the stack, it sits there on the stack till you change it. But passing passes on the stack. Therefore, if what you're really passing around is a pointer to an object, you're not changing the object, you're just making multiple references to the same object. Right? Do you see the difference? Do you see what's going on there?